Hey everyone, so we're on to the next one where we're going to talk about what's called Hooke's Law. Now, I want to remind you that each one of these new forces that we're going to talk about are only occur in very specific scenarios. So, we just learned about inclined planes. We're not going to bring that up while we talk about Hooke's Law. Hooke's Law is its own unique thing. Now, Hooke's law is actually, for the most part, it's the equation that we use that relates to how much force we apply to a spring and how much that spring stretches. This was done by a scientist named Hooke, as the name implies. He put masses on springs, found out how much it stretched, and kept doing that. And he found that there was a very unique relationship between the force and the stretch. So the equation of Hooke's law is Fs equals Kx. Now, Fs is the spring force. It is measured in newtons. I'll just write that here. K is what we call the spring constant. This is going to be measured in newtons per meter. And X is the spring length. And this is going to be measured in meters. So K is the spring constant, X is the spring stretch or the spring compress, however much the spring length changes, and Fs is how much force is applied on that spring. Now, the Fs, the spring force, is sometimes also called a restoring force. The main reason being the fact that the point of the spring force is always to try and bring it back to that original position. So when the object is just when the spring is unstretched and the object isn't moving, it's in that equilibrium state. There is no spring force; it's just hanging out here. But once you move it either to the right or to the left, the spring force will pop up and try to bring it back to that equilibrium position. So you pull it to the right, the spring force tries to restore equilibrium by pulling it to the left. You pull it to the left, the spring force tries to restore that equilibrium position and push it to the right. All right. Some other things that I want to say since I don't have them in here. The spring constant, this is referring to how rigid the spring is. So a spring that has a very high spring constant usually means that it's a very rigid spring, while a spring that's very low spring constant is a very loose spring. A good example is a slinky. A slinky typically has a very low spring constant. It doesn't really require that much force, and you can easily change its length. But something in a ballpoint pen or maybe even in the bed springs of your bed, those typically have much higher spring constants since it's going to require a lot more force in order to compress them. And they might not even compress that much. Now, K is also a constant for the spring. So it's not something that's going to be given on a reference table or anything. Usually they'll either have to tell you or you'll be looking for it. But for the most part, when you use this equation, it really is a very generic plug and chug type setup. All right, so here's the first question. Pause the video work itself. We'll go over in a second. All right, so here they want to know what is the spring constant based off of this graph. So the main idea that you want to do is take the slope of this. Now you could just take numbers and put them into the equation Fs equals Kx, but again, I recommend that you don't do that because there's going to be some cases, I believe in this topic, if not in this topic, definitely in the next one, where if you do that, you will get the question wrong. So what I would do is if you rewrite this equation, solving for k, you would see that you're basically dividing the y value by the x value, which is just another way of doing slope. Because remember, slope is just change in y over change in x. So if we do that, I'm going to pick this point and this point. So I have 2 minus 0 newtons divided by zero point 0.2 minus 0 meters. So when I plug that in, 2 divided by zero point 0.2, I end up getting 10 newtons per meter. You could also see it in the units that you're dividing them, so it's going to be a slope. All right, here's the next question. Pause the video, work itself, and we'll go over in a second. All right, so here they want to know what the value of the spring constant is. So again, the only way we can figure out the spring constant is by using the equation Fs equals Kx. If I look at the forces acting on this, we know that we have the force of gravity pulling it down equal to 5 newtons, and we have a spring force pulling it up. Because the object is hanging and it doesn't seem like it's moving, oh, it's here it is, it's at rest, we know that Fs and Fg have to be equal. So this is also 5 newtons. So when I plug this in, I have 5 newtons equals K times 0.075. So I get that the spring constant ends up being equal to about 67 newtons per meter. Again, you want to do the whole FBD. That stuff doesn't change. It's just now we're bringing in this new force that we can talk about. Here's the next question. Pause the video, work itself, and we'll go over in a second. All right. So remember, when we do stuff with the spring, we have our spring force of 16 newtons. We're once again looking for the spring constant. In order to actually solve this, I need to know what x is. Now remember, x is the change in the spring length. The spring goes from 10 centimeters to 18 centimeters. So its change is going to be 8 centimeters. Now here is the interesting thing. Because I don't specify what units it has to be in, you can actually keep this in centimeters. If you wanted to, you would end up with something like this, 16 on this side and 8 centimeters over here. And you'd end up getting 2 newtons per centimeter. Notice how the unit now changes since I didn't change this. Because there is no other meters anywhere in here, I could actually leave it like that. And the fact that the units are literally just this divided by this, it all works out. If you wanted to just be safe though, because this doesn't work all the time, you would have to move the decimal place 2 times. It would be 0.08 meters. If you redid the math with this number, 0.08, you'd end up with, I believe it would be 200 newtons per meter. So either one of these would be acceptable. A lot of times you have to pay attention to what units the choices they give you are. If the choices are all in newtons per centimeter, no conversion necessary. They're all in newtons per meter, definitely make sure you convert. Here's the next question. Pause the video, work itself. We'll go in a second. All right, so once again, in order to find the spring constant, I need 2 pieces of information. I need to know the force, and I need to know the change in the length. The change in the length is easy. They give me the original length, they give me the new length, so the difference is going to be 0.019 meters. Now, as far as what the spring force is, since they don't tell me any numbers with newtons, I'm going to want to draw my FBD. So this object is just hanging from my spring. Gravity's pulling down on it with a force of 1 kilogram is the mass, so it's going to be 10 newtons of force. And I know that my spring force is pulling up. So the force of gravity, the spring force, had to balance out. So this should also be 10 newtons. Using the equation Fs equals Kx, 10 newtons equals K times 0.019. I get a spring constant of 526 newtons per meter. Now you should start to notice that these questions are gradually getting more difficult, but they don't get that much more difficult. In fact, this is probably the toughest spring question that you'll see. A question where you're not given a force explicitly, you're not given the x value explicitly. You'll have to do a little bit of tiny minor math in order to figure it out, like subtracting these and multiplying this by 10. But for the most part, it's not really that hard. Most of these questions are plug and chugs and graphing things. So if you have any questions, please let me know. Otherwise, good luck and I'll see you later.